Okay, in this video we're going to look at how we can use the binary number system to represent negative numbers. At the end I'll show how we can use that to perform subtraction using binary. Okay, so we have two options available to us, which is the excuse me, sign and magnitude. So the sign and magnitude method and 2's complement. Okay, those are the two methods that we're going to be looking at. We'll look at the advantages and disadvantages of each one. Okay, so moving on to the sign and magnitude. The idea behind the sign and magnitude is we take a bit that will represent the positive or the negative symbol, indicating whether or not the number we're dealing with is positive or negative. Now, most commonly that would be the most significant bit, so the bit to the left-hand side of our number, and we would normally use 0 to represent the plus sign, a positive number, or the 1 to represent the negative sign, or to represent a negative number. So if we look at an example, if I've got the number 0, 1, 1, 1, okay, and we take our column headings as per usual, so we've got the 1 column, the 2 column, the 4 column, and the 8 column is going to be our plus or our negative symbol. Okay, so this number, because this is a 0, and in this system we've decided that 0 will represent the plus sign, or a positive number, we have 4 plus 2 plus 1, which gives us 7, and this is of course positive. To represent negative 7, we simply add the most significant bit, or set it to positive. So we would have 1, 1, 1, 1, okay, and that will equal, what is my ball doing? And that will equal negative 7. Okay, so aside from the funny hieroglyphics that my whiteboard has decided to add, here we've got an example of a negative number and a positive number in the sign and magnitude method, using the sign and magnitude method. Now, it's not without its problems. So if we just going to see if that sorts it out a bit. The obvious problem we've got is that this bit is given over to representing that symbol, and therefore we lose the possible range of the number of values we can represent, because we have one bit that is given over to representing the positive or the negative symbol. And another problem that will occasionally rear its ugly head is that we could have, which would equal positive 0, and we could have, which could equal negative 0. And having a positive negative 0 doesn't really make sense, and also can cause problems in the case of comparison. So if you compare this 0 to this 0, they will return false, then they're not considered to be equal, when in fact 0 would be equal to 0. So the sign magnitude system, it works fine, but it does have some shortcomings. On to 2's complement. Now, the 2's complement is a way of representing a negative number in binary, whereby the most significant bit, the bit on the left-hand side of the number, is considered to be negative. It takes its values, but as a negative value. So again, if we're working a simple small number, the nibble, the 4-bit binary number, I've got my 1 column, I've got my 2 column, my 4 column, and my 8 column is going to be negative 8. Okay, so if I were to represent the number 2 in regular binary, I just simply 0, 1, 0, 0. Okay, And just as with the normal binary system, that would represent 2. Now, to convert a number into its negative equivalent, its complement, there's a method, and I'll get to the method in a moment. I'll show you how we represent, how we represent -2, and then how we can make that conversion very easily, and a method that works for all numbers. So the negative would be, okay, so if we look at that, we've got -8 plus 4 plus 2, and -8 plus 4 plus 2 plus 6 will equal -2. Okay. Now, with smaller numbers, that's fairly straightforward. But the method I'm going to show you, just for what I did in my head, works for all numbers, all positive binary numbers, when we want to represent them as 2's complement. As long as we remember, our most significant bit is the negative number, and this will work. Okay. So what I did was, you start at the least significant bit, and you go as far as the first positive bit, the first 1, and you leave that 1 as it is, and then you flip all of the rest of the bits. So I go to here, that's a 0, so I ignore that, I go to the next one, that's a 1, that's my first positive 1, and so I leave that, and then I flip the rest of the bits. And as you see, that results in the same number that I used earlier, which we've already proven is -2. Okay, let's try another. So just again, I'll stay with nibbles for sake of ease, and because I've got them drawn out. Okay. Tidy that up a bit. Okay, so that is equal to 5. Agreed? So that's 4 plus 1 equals 5. Okay, so the method, we move from least significant bit, first positive bit we find, we leave, and we flip the remaining bits. So we go 1, 1, 0, 1. Now this should result in -5. So we take -8 plus 2 plus 1. -8 plus 3 is equal to -5. And there's our answer. So remember those steps. We start with the least significant bit, get to the first positive bit, leave that unchanged, and then flip the rest of the bits. And that will give us our 2's complement representation of the complement of our positive number that we started with. So we've got from 5 to -5 using that method. Okay. Finally, looking at subtraction in the binary number system. And what we would do is, in fact, take, say for example, we wanted to say 5 minus 3. We wanted to calculate 5 minus 3. Again, I'm keeping it nice and simple with small numbers. Okay, what does that equal? And we want the computer to carry that out. Well, we take the positive binary numbers of both. Okay. So, and I'm going to work in nibbles just to keep it tidy. Okay, so 0, 1, 0, 1, 4 plus 1 is, we start with our 5, and we take our 3, which 3 is 0, 0, 1, 1. Okay, 1, 1, 1, 2, added together we get 3. And we take the 2's complement representation of 3, this is positive 3, and we want to convert it to -3. So remember the technique. We move least significant bit, we start here, we get to the first positive bit that we find, the first 1 value, we keep that the same, and we flip the rest of the bits. Okay? So then we take this result, we take our 2's complement number, and now we are adding -3 to 5. Okay, remember that a basic processor can only perform, the arithmetic logic unit can only perform addition. Now obviously you might get some real techie saying, no, that's not the case, but I'm talking about very, very basic, okay? So 1, 1, 0, 1. So we perform the binary addition to this, okay? So, binary addition, as if you've seen other videos, you'll know how this works. So a 1 and a 1 gives us a 0, and we carry the 1. This will give us 1. Okay? We've got a 1 and a 1, so 0, carry the 1. Here we've got 0, but we've got 1 and a 1, so again 0, and we carry that 1. Now this gives us a problem of overflow. We've only got 4 bits, so we just ignore this one. Get rid of it. Okay, now I'll erase this working space. And we should have the correct answer, which is 2. Which 5 minus 3, we know, is 2. So that gives us the correct answer. And that is how we would add, or rather we would subtract, we would add a negative number in binary to perform subtraction in the using the binary number system, using the 2's complement method. And that's it. I hope that's been useful. Any questions? Please let me know.